We're now going to be moving on from exponentials and having a look at our logarithms. So logarithms are another way of thinking about our exponents. So in this case, we can say that a logarithm is simply an index or a power. So you might not know this yet, but we are going to explore this a little bit more. So for example, we know that 2 raised to the 4th power equals 16, right? 2 times 2 times 2 times 2, that's equal to 16. And of course, this is expressed by the exponential equation 2 to the power of 4 equal to 16. We know this. And we've been working on and doing kind of things like that over the last week or so. We could also think about this question by asking, well, what is 2 raised to what power gives us 16? And so we know from here, well, 2 raised to the 4th power is equal to 16. And this is expressed by the logarithmic equation log of 2, 16, is equal to 4, which reads log base 2 of 16 is 4. So pretty much what we can say is that these two different equations are actually, I guess, equal to each other. They kind of mean the same thing, they're equivalent. So these two equations here are describing the same relationship between 2, 4, and 16, where 2 is the base for both of these, and 4 is my exponent. I guess the difference being that the exponential here isolates the 16, whereas the log here isolates the index 4. Here are a few additional examples about the exponential versus the logarithmic statement, as well as an alternative exponential statement. So this is saying 2 to the power of log base 2 of 8 is just equal to 8, and 3 to the power of log base 3 of 81 is equal to 81. Then 5 to the power of log base 5 of 25 is equal to 25. So you might notice a bit of a pattern here, and we are going to look at that a little bit further down below. So all in all, we can say that in general, the formal definition of a logarithm is that any log of base a to the b is equal to x. And of course, from our exponentials here, we know that a to the power of x is just equal to b. So for all of these, we can see that my base is a, x is my exponent, and b is what we call the argument. The argument being this 8, 81, 25, or back up here where we saw that my argument was 16. We can now have a look at some of our special cases as well. So sometimes we see something like this where it just says log 10 to the power of x is equal to x. And we can see in between, there's not this log base of a or anything. In this case, we will always assume that if there is nothing written next to my log, then I'm going to assume that this is a log base of 10. And this is kind of what it gives us in this case. The other thing that we want to look at is from back up here when we're talking about our different types of statements, and we get it from here. So this gives us something that is known as the inverse property. So we know that a to the power of x is equal to b, so that's from here. And we know that log base a of b is equal to x. So this we know are equivalent statements, as we said beforehand. If we substituted 1 into 2, then we'll actually find that we get this argument down here, our inverse property, where we're saying that x is equal to log base a to the x, or log base a of a to the x is equal to x. And this is what I was talking about up here when we're thinking about, you might have noticed a bit of a pattern where if we have the same base for our log and our exponential, it's actually just equal to this argument over here. And this actually allows us to start cancelling out and using these to our advantage to solve some equations. So as I said before, this is known as our inverse property and allows us to cancel out a log base a of a as well as our exponential here. So further analysing these alternative exponential statements from the ones up here, we can further say that the inverse property, so if we had a to the power of log base a of x equal to x, again, we can cancel out this a to the power of log a to just give us x left over. So rather than having the log base, we've now got a exponential base, kind of. So we've got the a to the power of rather than log base a of a to the power of something else. And of course, if we're looking at our special case where we assume that if there's nothing next to my log here, then it's base 10. So to be able to cancel out this log base 10, then I need to raise this with a 10 to the power of log x equal to x to be able to cancel out this 10 and log base 10 here. We're going to now have a look at some examples.
Let's now have a look at our different examples for the definitions of our logs. So we've got the log of 3 is equal to 243. So let's actually find what this is. Now what I want to do is I'm going to factorize this 243 here. So I can say that 243 is equal to something, and what I want is to actually have it so that it's to the power of 3 because of this log base 3 here. So I want, what do I have to have 3 to the power of to get 243? And using your calculator, you'll find that this is to the power of 5. So then, therefore, rewriting this first initial thing, I can say that log base 3 of 3 to the power of 5 is equal to, now remembering just beforehand we established that if we've got ourselves our log, log a base a of a to the power of x, this is just going to be equal to x. So this implies that this kind of bottom bit here cancels out. So we've got the same thing here. We've got log base 3 and then we've got 3 to the power of something. So this implies that this cancels out and actually just gives us an answer of 5. So this up here is equal to 5. We're going to be using this same rule here for the rest of our examples. So having a look here, I've got log base 5 of 0.04. So again, I want to look at rewriting this part here, this 0.04, so that it's the power of 5, or well, something with the base of 5 to the power of something is going to give me 0.04 here. So we can say that 0.04 is equal to 5 to the power of something. I do not know what it is just yet. However, if I put this into my calculator, this actually gives me that 1 over 25 is equal to the 5 to the power of something. And we know that I can write 25 as 5 to the power of 2. So I'm going to have 1 over 5 to the power of 2 is equal to 5 to the something. And I know that using my index laws, this is 5 to the power of minus 2 equal to 5 to the power of something. So I've now written this 0.04 with a base of 5. So putting this back in, I might put this over here. So that means I can say that log of base 5 of 5 to the power of minus 2 is equal to, and remembering back from that rule that we established earlier on, that these two can now cancel each other out. And this is just equal to minus 2. So my answer of log base 5 or 0.04 is actually just equal to minus 2. Moving on, this one's a little bit more tricky, but again, we want to think about how can I rewrite this so that I have a something to 2 to the power of something giving me this answer here. So if I write this out, so if I had here my 5 square root of 4, and I actually know that this is the same as 4 to the power of 1/5 from our index laws. And I know that this 4 here can be written as 2 squared. So putting this back in, I've got log base 2 of 2 squared to the power of 1/5, right? And I want to simplify this a bit further using my index laws. So I've got log base 2 of 2 to the power of 2/5. And this is going to be equal to, so now using that rule again, I can cancel these two out. And this is actually just equal to 2/5. So this answer here is 2/5. Alrighty. Looking at these two examples here, remembering that if there is nothing next to my log here, then this implies that it's a log base of 10. And that's going to be the same for these two here because there's no log base next to this. So I'm just going to assume that this is log base 10. So this tells me that, of course, once again, I want to factorize this part here so that it gives me something to the power of 10, or 10 to the power of something is going to give me this 10,000 here. But this should be pretty simple. So if I have log of the implied 10, so if I did 10 to the power of 1, 2, 3 to the power of 4, okay, this is going to give me some number here. So of course I've got this log base 10 here. So these two cancel out and that's just going to leave me with 4. So my answer for this one here is 4. Same thing, I'm going to rewrite this. So this is going to be equal to log of, and here I can say that this is 100 to the power of a third. And I want to write this 100, of course, as a base of 10. So log of 10 squared of 1/3. And then this is log of 10 to the power of 2/3. And again, we know that there is a base 10 implied here. So because of that, we can cancel this out. And I'm going to get a final answer of 2/3. So this here is just equal to 2/3. Moving along to a few of our final examples here. This wants us to write the following here with a base of 10, where this x here they want correct to 4 decimal places. Now this we can establish, or we can be able to write these by using the following rule, which pretty much tells us that if we have a 10 to the power of log x equal to x, then the same kind of thing, I guess these two kind of cancel each other out here, but we're just going to kind of use this identity or this rule here to figure this out. So in this case here, my 6 is my x's. So I'm going to have 10 to the power of log 6 is going to actually give me 6 here. And what I'm going to do is, using my calculator, I'm going to figure out what log 6 is. So in my calculator, I should have had that log 6 is 10 to the power of 0.7782. So we can see here that my answer is to 4 decimal places as asked in the question, so that's all I've got to do. We're going to do the same thing for these other ones. So in this case here, I know that this is going to have to be equal to 6,000 of 10 to the power of log 6,000. And this, using my calculator, is going to be 10 to the power of 3.7782. And finally, having a look at this very last one, I've just got 0.06 is equal to 10 of log 0.06. Evaluating that in my calculator gives me 10 to the power of minus 1.2218. And we're done. Now having a look at our very last example here, I've got explain why log 5,000 is equal to 3 plus log 5. So what it's asking us is, how can I prove that my left-hand side of my equation is equal to the right-hand side of my equation here? Now, of course, this one is a little bit trickier. We can see in this case that it doesn't have a base written, so I know that this implies that it must be a log base of 10. So what I'm going to do is I want to think about, well, how could I factorize this part here? Oops. How can I factorize this 5,000 to be a base 10? So if I write this out, so I'm going to have that log of 5,000 is equal to, I'm going to break this up as 1,000 times by 5, because remember, I'm trying to think, what can I do to turn this somehow into 10 to the power of something. So this is then going to be equal to, obviously I need to have 10 to the power of 3. And remembering, we need to use this rule again, so we need to have that my 10 to the power of log x is equal to x, and my x in this case is going to be this 5. So this is going to be 10 to the power of 3 times by, and I'm going to have 10 of log 5 up here, like so. Oops, and I've been really silly and I've forgotten to write log before all of these. So let me just move that over. Log, there we go. Now we can see here, because of course this is an implied base 10, I'm able to cancel out these two base 10s here. So this is going to leave me with 3 plus log 5. Okay, so remembering back from when we did our index laws, that if we've got two bases that are the same, so a to the n times by a to the m, this is going to be equal to a to the n plus m. So in between here, if I did show an additional step before I cancel these out, I would have had log of 10 to the power of 10, 3 plus log 5 using this rule, and that's how I got this final 3 plus log 5. And as you can see here, this answer has proven that my left hand side is in fact equal to my right hand side. So that's just one example of how I can show that these two are the same as each other.